today's lecture basically on fluid flow through pipe. So when you are discussing about fluid flow through pipe, we have to understand the surface properties of the pipe, material of the surface, and how it is affecting the fluid flow. And you have to understand how the fluid is flowing from wellbore to the surface. Although some brief description already given, but for this lecture I will be starting with brief from reservoir to separator, how the fluid is flowing. So first, assume there is one reservoir and there is one wellbore and you have one tubing. So whenever you are getting oil and gas, you are producing through tubing actually, and your casing is cemented here. And when you cemented the casing, actually you are not getting production, so you have to perforate it, or you have to create lots of holes or pores in the tubing after cementing, so that fluid will be entering through the through the pores to the wellbore, and it will be passing through the tubing and it will reach to wellhead. This is wellhead. From wellhead it will go to one choke to separator. Choke to separator. Now, when fluid is flowing from wellbore to the separator, there will be lots of resistance. It will cross, and if it is having very high viscosity, it will have very high resistance. If it is having lower viscosity, for example water will have lower resistance. But if you have viscosity say 10 cp, 20 cp, 100 cp, so as centipoise or viscosity unit, if the viscosity is increasing, it will have more resistance, and resistance is related to your fluid friction or surface properties. So today lecture I will include all this viscosity relation with surface phenomena, and how this laminar to turbulence fluid is having different pressure drop. Okay, now last lecture we have seen IPR, inflow performance relationship, where we have seen this flow rate and PWF, flowing pressure. Flowing pressure means in just entry at the tubing, the pressure, if we measure when fluid is flowing, that is called flowing pressure. And how much fluid is flowing, if I denote using symbol Q, then the IPR curve will be like this, straight line, or maybe curved. IPR curve will be straight line if it is single phase liquid flow, but if it is having gas or it is creating two phase flow or condensate reservoir, in that case it will not follow the straight line curve, it will be curved. In some cases maybe initially it will be straight line and later it will be dropping with the curve. So that will be curve for reservoir fluid flow. And reservoir fluid flow means it will be getting resistance because of pores and the connectivity between pores, that is called permeability. And there will be resistance in between the reservoir and the wellbore. There will be sand phase completion or sand control equipment and other equipment will be there. Because of that, the fluid will be getting resistance. Now we got fluid into the wellbore. Now the wellbore will be allowing fluid to move from reservoir entry to the surface or wellhead. When it is reaching to the wellhead, so there will be certain pressure drop, and if you do not calculate the pressure drop, so you may not be able to maintain pressure at the wellhead or at the choke or at the separator. Why the maintaining pressure is required? Because separator needs certain amount of pressure. If you are not maintaining certain pressure or velocity or flow rate, then the separation efficiency will be very lower. Again, in choke, performance will be also changing. So to maintain pressure, you have to understand where the losses are there and how much fluid flow is there, what if the tubing size is there, or how much gas will be evolving or coming out from the wellbore if pressure is changing. For example, pressure drop is very high through the piping, so initial pressure may be 1000 psi, then when it is reaching to wellhead, it will be 10 psi or 20 psi, 30 psi. So because of this very high change in pressure drop, so there will be bubbling out, that bubble formation will be there from the oil, and oil will give lots of gas, and when it is giving gas, then your fluid property will change. Maybe the wellbore will not be able to produce oil or gas. Because of this, gas and liquid will be accumulation, liquid particle will be held up at the bottom, and when liquid particle is held up at the bottom and liquid column is getting growing up, after certain time the hydrostatic pressure of the liquid will be equal to reservoir pressure. In that situation there will be no inflow. Okay, so although you have everything all right, but because of this liquid column development, your fluid will not be flowing into the wellbore, so your production will be stopped. So that is called liquid held up condition. So you have to know the pressure drop through the pipe. Start with flat plate. Let's start with pipe flow. So you may have studied this pipe flow, laminar flow, transition flow picture. You can remember this one. Okay, this is velocity u, and fluid will be developing like this, and laminar zone will be like this, and fully developed zone will be looking like this. This is the velocity. The central line velocity will be higher and nearby wall velocity will be lower, and this is called laminar. This is developing flow. Developing flow. And when, if you see from the center line of the pipe to the wall, the fluid velocity is going down and down and down. Okay, so fluid velocity, if you see here, you see this line shows amount, the magnitude of the velocity. Okay, if you are reaching towards wall, velocity is going down. Why it is going down? Because we assume the near wall of the pipe, fluid particle will not be able to move because of friction. Because of friction, particle is not moving, and when particle not moving, that means velocity is 0. And when you are going away from wall, so particle will be sliding, the fluid particle, one layer is here, this is not moving, another layer will be here, that layer will be moving over another fluid layer. So different fluid layer will be moving one by one. So that's why near wall you are getting 0 velocity, but when you are moving up, you are getting higher velocity. Again you reach at the center of the pipe, now again you are moving up, again your velocity will go down, and you will be reaching to the upper wall or another wall of the tubing. So in that case, your center velocity very high, but wall velocity is 0. So when wall velocity is 0, normally it is called no slip condition. No slip. Okay, no slip means we are assuming the particle is not slipping, it is sticking, and velocity is 0 on the wall. If it is not sticking, then velocity will not be 0. Next thing is that Reynolds number. Reynolds number, or normally people will be representing as Re. Sometimes people will say Ren, some other terms also can be used. So normally we say Re means Reynolds number. So rho V d by mu, or V d by mu. Okay, so rho means density of the fluid, V means velocity of the fluid, d means diameter, and nu is kinematic viscosity, and d is dynamic viscosity. Okay, this is non-dimensional number. Non-dimensional number. Okay, so if you take any unit, it should be non-dimensional. If it is coming with some dimension, that means your rho unit you have to change, or V or D or mu unit you have to change. Okay, if you take coherent unit, then it will be non-dimensional. So every time you have to remember, whenever you are calculating Reynolds number, you have to make it non-dimensional. If you are not making, then there will be some error, some problem, especially in field unit when you are doing. So you have to be careful to use Reynolds number. Now rho is inertia force by viscous force. This is showing first the top term. This term is inertia. This is viscosity term is there, so it's called viscous. So how much fluid is trying to move, but because of viscosity it is getting reduced. So that ratio is Reynolds number. Now Reynolds number, when it is laminar, normally it will be 2000 or 2000 Re less than, and Re more than 4000. So we will be calling turbulent flow. This is laminar. Okay, so and this is valid for pipe flow only. And if you are using open channel flow or other type of flow, for example, you have some open channel flow, in that case Reynolds number will be different. presently we are focusing mainly on pipe flow, closed conduit, circular duct. For that, laminar flow will have Reynolds number less than 2000 and turbulent flow will have more than 4000, and in between the 2000 to 4000 we call transition flow. Okay, in between there will be then RE 2000 to 4000 called transition. Okay, you should remember these values. This is very common term. Many time, many interview or many exam people will be asking what is the value. Roughly you have to remember, because exactly 2000 we write, but it may not be exactly 2000. Sometimes some books will be writing is 2300. Sometimes this 4000 term they will be writing 3800 or 4300. But approximately is 2000, and turbulence range will be 4000 plus approximately. So it is a inertial force by viscous force, and you have to remember the formula also. Normally we will not give the formula during the exam, so you have to remember the formula. It is non-dimensional number. If I give unit in different units, which will create dimensional Reynolds number, so that will be wrong. So whenever you are calculating, you have to check units are okay, or after calculating you have to check with Buckingham-Pi theorem whether you are getting non-dimensional Reynolds number. Okay. Okay, whenever you are talking about fluid flow, pipe flow, so we talk about friction. When we are talking about friction, that means you have to understand how the fluid is flowing over a flat plate first. Okay, so let's assume this is a flat plate, and you have seen in all the thermodynamics book will have this picture, I think. Okay, this is called laminar zone. This is called laminar. And fluid velocity, let's say initially uniform, and when it is entering on the flat surface, let's say this is flat surface, fluid is coming at uniform velocity. When it is reaching, it will create one layer on the fluid's solid surface, and next layer will be like this. Next, so the initial will be laminar, then after that there will be a transition zone, then after that the transition zone will be broken, it will be creating loss of turbulence, so that is called turbulent zone. So here I'll draw like this, laminar or entry length, entry, then this area will be turbulent. Okay, this is transition. Okay, so laminar zone or inlet zone, the velocity will be very much uniform, then slowly maybe it will try to deviate from the smooth flow path. Okay, then when you are reaching to turbulent area, the particle will try to move randomly, so that is turbulent. Okay, so it is like this, and if I draw velocity profile in turbulent zone, it will be like this. Okay, and there will be near wall very thin layer will be there, that is called viscous sublayer. Sublayer, and there will be another layer, then this will be fully fully turbulent layer. Okay, so our basically friction will come because of viscous sublayer. If you go to turbulent layer, it is away from the wall, so that is not affecting so much, but viscous sublayer is affecting. But because of turbulence, the viscous sublayer will be getting affected because it will increase length or decrease length because of this turbulence creation. Later we will discuss how it will be affected by the surface properties. And now surface roughness. Whenever we talk about surface roughness, and if you see any surface, for example this mobile device is there, and it is having, in naked eye you can see this is smooth surface, but if you take one microscope, actually the surface is not smooth, you will find lots of regions, valleys. For example, let's see this surface. Okay, by naked eye you can see like surface maybe a little bit rough like this. Okay, surface will be like this. Okay, but if I take a microscope and if we just see the same surface, so surface will be like this because it is enlarged. Okay, so that means all surface whatever we see in our naked eye, so that apparently it is looking like very smooth, but microscope or electron microscope, anything very high resolution picture if we take, it will say lots of ridges and valleys are there. So that is called roughness. Okay, so the roughness will give more friction, and I can give one example how roughness is affecting the fluid velocity. Okay, roughness will reduce your fluid velocity, it will give more resistance to flow, and pressure drop will be higher. How? Let's say you have one bike and you're driving on a road, rural road, and road is very much uneven. Okay, because of unevenness, actually your bike will be using same fuel, but bike speed will be lower, because there's lots of unevenness is there, and bike will be making like up and down, up and down, up and down. Because of this up and down motion, randomness is there because on the road, so your velocity will be going down, and because of that your energy consumption may be same, but your speed is reduced. So that is pressure drop actually in fluid flow term. So if you take fluid flow and it is flowing over uneven surface, it will have lots of resistance, and the reason of resistance is like this. When fluid is flowing at a smooth surface, this is smooth. Okay, this I told her this is, if I see in the microscope, then we can see rough terrain or rough surface. But if we take certain surface which is having already roughness like this, okay, if certain surface is having already rough, for example cast iron normally you will have surface is very rough, but in some cases, like say if you have some blade, the surface is very smooth, or mirror surface is very smooth, or your computer screen is very smooth. Okay, so when surface is very much rough, the fluid will be having difficulty to flow over it. How? Like when it is flowing, let's say on the surface there will be one viscous sublayer. This is viscous sublayer. You see the sublayer, and here another viscous sublayer. When fluid is flowing over smooth surface, so your viscous sublayer and your surface roughness, there is some gap. Surface roughness is here, but your layer is here. So because of this layer is here, so fluid particle will not get affected by this your roughness. But the second picture, viscous sublayer on rough surface, what happens if surface is very much rough and sublayer is created here? So what will happen? The particle will be interacting lots of time with this ridge and valleys. Okay, when fluid particle likes to move on a smooth and straight path, when it is getting some stopper or say ridges or valleys, so what will happen? Fluid will go move up, sometime down, sometime move up and down. Because of the move up and down, it will lose energy, it will lose its velocity. So fluid will get more resistance, pressure drop will be much higher. So rough surface will give more resistance, so fluid will not be able to flowing smoothly. But when you are having smooth surface, fluid will have a smooth laminar layer will be created and smoothly be flowing. So viscous sublayer, if higher than your surface roughness, then we can assume this is smooth surface. And if roughness height is crossing viscous sublayer, there is a rough surface actually. And when we have viscous sublayer more than my roughness value is changing up to certain level, it will not affect so much my fluid flow. But roughness is crossing viscous sublayer, it is crossing very high, then in that case your fluid pressure drop also will be affected by your roughness. So one term we call hydrodynamically smooth surface. Hydrodynamically smooth surface. So we say hydrodynamically smooth surface. Hydrodynamically smooth. So hydrodynamically smooth surface is that when viscous sublayer and your surface roughness is having just some distance. So that is hydrodynamic. So if your surface roughness is changing up to certain level, it is not reaching to the sublayer, then it is hydrodynamically smooth. So if you are changing some roughness value, it will not affect your fluid pressure drop or friction. But when you are crossing that hydrodynamically smooth range, so in that case your surface roughness will be affecting your fluid flow and pressure drop. So one term is used called sand roughness number. So to approximate this roughness, so people will be assuming how much, let's say, sand particles are there. Okay, so the term they are using sand roughness. Okay, when fluid is flowing over it, whether viscous sublayer is crossing this one or it is away from the sand, the larger diameter. So that way they will be defining and they will be calculating just to approximate roughness. Otherwise, if you want to take actual roughness, it will be having lots of peaks and valleys. So then you have to calculate RMS value of the roughness, and that also creates very much complexity. So people will assume this sand roughness. So they will assume the sand particles are there. Because of sand particle, it is getting roughness, and fluid flow and pressure drop is changing. Okay, when you talk about pressure drop, you have to think about shear stress. So shear stress tau equals mu du by dy. Mu is viscosity. Mu is viscosity, and for Newtonian flow, we assume mu is a constant term. But if you use non-Newtonian flow, so in that case mu may not be constant. So in that case, we have so shear rate, and this is shear stress. So for Newtonian flow, the curve will be like this. Newtonian flow. And for dilatant flow, and another is pseudoplastic. Okay, so if you study rheology of the fluid, of Weilburg fluid, so you will find it is sometimes it will be behaving as Newtonian flow, sometimes it will be behaving as a non-Newtonian flow. At certain condition, fluid can be Newtonian flow, but after certain condition, it can be more non-Newtonian. For example, if you have more wax, because of temperature and pressure change, and you get more wax is settling down, so in that case it will behave as a non-Newtonian fluid. Again, Weilburg fluid actually mixture of many component, many fluids, actually many hydrocarbons, maybe low carbon, shorter chain of hydrocarbon, longer chain of hydrocarbon. That's why it may not be exactly being plastic or dilatant or Newtonian flow. It will be mixture of something. But if it is following certain curve, then you can assume, okay, this is a Bingham fluid, or this is a Newtonian fluid and non-Newtonian fluid. So crude oil, sometimes we consider non-Newtonian, sometimes it is called Newtonian. And if it has more wax, so normally it will be non-Newtonian flow.